I'm going to work out the 5 questions on the in-class quiz from Friday. This first question was to make sure that you understand the relationship between Ka and how weak or strong an acid is. So here's a little summary for you. The larger Ka, the more acidic the acid is. So think for a minute if we have a generic weak acid and the products for a weak acid are hydronium ion and the conjugate base, okay? So the more hydronium ion you have, the more acidic this acid is, okay? And to get more hydronium ion, you need a larger Ka. Because remember, Ka is products over reactants. So right away, you should be able to tell that hydrofluoric acid is less acidic than hydrogen sulfate ion. Okay? But you can't immediately compare these two because it's given you pKa's instead of Ka's. So you need to convert those pKa's to Ka's before you can completely compare them. And I'll do that on the next page. All right, so first thing I want you to know is that P of anything means minus log of whatever that thing is. So if it were pH, it'd be minus log of H concentration. In this case, pKa is minus log of Ka. If we're trying to go in the other direction, if we're trying to solve for Ka, it's the reverse, which would be 10 to the minus pKa. So now let's convert those pKa's on the previous page, 12 and 4.76, to Ka values. So for pKa of 12, that would mean the Ka is 1 times 10 to the minus 12. That is the smallest Ka value so far, weakest acid. Okay, means not very much of it dissociates at all. pKa of 4.76 means that that Ka would be 10 to the minus 4.76, and that comes out to be 1.74 times 10 to the, let's see, 1, 2, 3, 4, 5, minus 5. So instead of backing up to the last page, what you can do just to verify that you understand is put the 4 Ka values you have, these two and the two that were given as such on the last page, from the smallest Ka, which would be the weakest acid, that's the one with the most negative exponent, to the strongest Ka, strongest acid, which would be the one with either a positive exponent or the smallest negative. The first thing you need to ask yourself when you're trying to find the pH of something is whether or not the something you're talking about is strong or weak. And that's simply memorization. So HCl is one of the strong acids. Why is that important? Because a strong acid does not have an equilibrium, does not have a Ka, and it's much easier to deal with. A strong acid dissociates 100% into the ions. So you end up with the hydronium ion and the conjugate base, and whatever concentration that you started with of the acid, in this case 0.0225 molar, turns 100% into the hydronium ion. So you end up with 0.0225 molar hydronium ion. And the original acid doesn't exist anymore. It's all dissociated. And now you simply remember your formula that pH is minus log of the concentration of hydronium ion. And you know, you've just figured that out, that that is 0.0225. And so you take the log of that and you get that pH equals 1.6 5. Messing up. I'm going to write a bunch of digits and then we're going to decide how many sig figs. So I'll just write a bunch down to begin with. Alrighty, so this is where I think a lot of you messed up, is you forgot how to determine the number of sig figs in a pH value. First of all, let's look at the number we started with, which is just, it's not a pH value, it's just a concentration, and I think most of you know that this number has 3 sig figs. Just a friendly reminder, leading zeros never count as significant digits, so 3 sig figs. All right, now when you're recording the pH value, you want to maintain the sig figs that you started with. So we want our pH number to have 3 sig figs also. To remember, in a pH value or OH or pKa, any P type number, digits to the left of the decimal do not count as significant. You can't leave them out. They're an important piece of information. They represent the exponent in the original number. But the only digits that are measured digits and therefore count as significant digits are those to the right of the decimal. So if we want 3 sig figs in this pH value, we want 1, 2, 3. Only the first 3 digits to the right of the decimal. So the correct way to report the pH with the correct number of sig figs, so you've got to show that one even though it's not a sig fig. 6, 4, and we're going to round this 7 up because next to it is an 8. That is how to correctly report sig figs. All right, I guess in each of these problems there's something that you need to be careful of. In this case, as I've always recommended before you try to work any problems out for acids and bases, go ahead and write out the dissociation reaction that occurs. First question, as always, is that a strong substance or a weak substance? That is a strong, one of the strong bases that you have to memorize, which means it dissociates 100% into the ions. If you're working with a base, you don't need to include water. The cation and anion can be shown dissociating without water. In fact, water confuses it kind of. So again, there's no equilibrium, there's no K value. Whatever concentration you started with is going to tell you how much of the product or the dissociated ions you have. In this case, I did not tell you the original concentration of barium hydroxide. The only information I gave you was pH. Whenever that happens and you're not quite sure what to do, like I said before, start by writing a balanced dissociation. Second, do some simple, obvious calculations. What can you do with pH equals 12.7? Well, I know I can work backwards and I can find out the concentration of hydronium ion from that. But I really don't want hydronium ion. Whoopsie daisy. I want the hydroxide. So I'm going to convert the pH to POH first. So POH equals 14 minus 12.7, which means POH equals 1.3. And now I'm going to go ahead and find the concentration of OH, and that's 10 to the minus 1.3. And that equals 0.0501 molar. All right, so what can we do with that? Well, what is the relationship between hydroxide ion concentration and the original concentration of barium hydroxide? Probably, there's several ways to do that. Some of you can do it intuitively, but let me show it as unit cancellation. So if I have this much molar concentration of hydroxide, and I set up my little T-chart, and I can say, okay, I have 2 hydroxides for every 1 barium hydroxide. And that means I have to divide the 0.0501 by 2, and then I get 0.025 molar as the concentration of barium hydroxide. And so that is C. This problem is a standard weak acid. Okay, HCN is not one of the strong acids. How do you even know it's an acid? It starts with hydrogen. Okay, it is a weak acid. Gave you the Ka. Number 1, draw out the dissociation in water of a weak acid. You have an equilibrium. All right, and 2, set up your Ka expression and your ice table. So I guess I'll do my ice table first. Water is not included in the equilibrium. My original concentration of HCN is 0.10 molar. The products are 0 to begin with. And they're all present in a 1-to-1-to-1 stoichiometry, so I'm going to call the change in hydronium and cyanide X and minus X for the original acid. And so my equilibrium concentrations are as follows. Write out your Ka expression, concentration of products over reactants. Now, they gave you the value for Ka, but now the big question is it safe to neglect X? You need to know when to do so, because even though I will not give you a regular problem to solve where you cannot neglect X, I may give you a multiple choice question which asks you which of the following is it safe to neglect X. So you need to understand when it's okay to do that. So let's look at the X we're thinking about neglecting right here. Typically, if the Ka is of the order of 10 to the minus 4 or more negative, then you're safe. And that's presuming your original concentration is not that small also. In this case, with the Ka of 10 to the minus 10 and a 0.1, which is just 10 to the minus 1, you're very safe in neglecting X. So I can go ahead and fill in my amounts now. I've got X times X as concentration of hydronium and cyanide divided by 0.10 minus X, and I've just decided it's safe to neglect X. And when you go ahead and solve that for X, you get that X equals 7 times 10 to the minus 6. Go back and read the question. Make sure you're done when you solve for X. This is asking for hydronium concentration, and in this problem, X does in fact represent the hydronium ion concentration. So you are done. I could have as well in this problem have asked for pH instead of hydronium ion concentration, in which case you would have had to take the minus log of this X. So just make sure you go back and read the question. Last question. This is a weak base. If you didn't pick it up before, anytime you see a nitrogen-containing compound that doesn't have a plus charge, it is a weak base. Okay, so you want to draw out your equilibrium, and this is the one exception where you do need to show water. And you make the ammonium ion and hydroxide. You'll always see hydroxide as one of your products if you have a base. I gave you the Kb value, so you set it up with a very similar style as you did a weak acid, but you have got to know how to draw this dissociation. All right, so I'm going to go ahead and write the ice table next. Again, water does not play a role in equilibrium. My original concentration of ammonia, and the products are 0 to begin with. Again, they're all present in a 1 to 1 to 1 ratio, so I'm just going to put minus x, x, x. Ask yourself, can I neglect x? Well, the KB, notice it's KB. If I would have tried to trick you and given you KA, you would have had to convert from KA to KB. So make sure you know how to do that. In this case, I didn't. It is safe to neglect X because KB value is more negative than 10 to the minus 4. And so I can now say that KB, 1.8 times 10 to the minus 5, equals x squared over 0.4. If I then solve for x, I get that it is 0.00268 molar. Now, as always, go back to the question and make sure that x is what they're asking for. This question is asking for the pH, so we are not done. What does x represent? It represents OH. Okay, so we're not anywhere near done. We have to take the concentration of OH and turn it into pH. So I'll do that on the next page. You can get to pH in a couple of different ways using that square calculation diagram I showed you. I am going to do it using Kw first. Concentration of hydronium ion is Kw divided by concentration of hydroxide. So that is 1 times 10 to the minus 14 divided by the concentration of hydroxide that we just calculated from the ice table. And so that equals 3.73 times 10 to the, hold on, I got to count, 3, 6, 9, wow, to the minus 12. All right, so that is the concentration hydronium, or H+, they're equivalent. So now the pH is minus log of that concentration, so it's minus log of 3.73 times 10 to the minus 12, and that is 11.43. And that was letter choice C on the previous page. So that's it for the quiz. These are good representative problems of what you can see on your test.